In this video, we're going to talk about exponential growth and decay. So whenever you're given a proportional differential equation, right, so dy over dx times, or k times some sort of value, because this means that it's proportional, you're multiplying, right? We know that the solution to this differential equation is going to be y equal to some sort of constant times e raised to the k times x. And we know this is true because if we solve for this differential equation, we will get this general solution. And we can do this by separating variables. So let's separate. So we multiply both sides by dx, so we can cancel this dx on the left side and the same to the right side dx. So we're left with dy is equal to k times y times dx. And then we're just focused on removing the y from the right side and moving it to the left side. So we're going to divide the right side by y, and this cancels the y on this side. And then we'll do the same thing by multiplying dy by, by 1 over y. So then we're left with 1 over y times dy is going to be equal to k times dx. Great. So now to find the solution, right, because the solution to a differentiable equation is the original equation, or the original function. And to find the original function, we have to antiderive. So we're going to antiderive both sides. And the antiderivative of y would just be the natural log of y is going to be equal to k times x plus your constant. Keep in mind that you only want to add your constant to one side. You can add it to the y side, to the left side, or the right side. I prefer to do it on the right side because that's how it's commonly referred to in textbooks and how you'll probably be taught in class. So then now how do we cancel this natural log so we can separate y? Well, we raise everything to the e. So we raise this side to the e, raise this side to the e. So then this e, because the natural log has a base of e, right? So there's an e here. These will just cancel out. So then you're left with y is going to be equal to e raised to k times x plus c. Now, if you go back to your power rules, you should have learned that when bases have the same base and they're being multiplied, right? So if you have an exponent with and then it's being multiplied with another value that has the same base, so these are both x, and they're both being multiplied, you're simply going to keep the base, however, you're just going to add the exponents, right? So this is going to be equal to x to the sixth power. And we can see here, right, as we have here, we have our exponents are adding. So if we're trying to move back, right, we can add, or we can separate these by multiplying them. So we can just do y is equal to e to the power of kx times e, right? Because we want to have that same base, to the power of c, right? So then you can see how these equations are really similar, right? Well, they are the exact same thing. However, you need to recognize that c is a constant, right? Because c is a constant, you can simply rewrite this as just c. That's just how it works, right? So then you have e to the power of k times x times c is all equal to y. And that is our general solution to our proportional differential equation, right? So, and if you remember back to pre-calc, this equation should look very, very familiar, which should look something, or you should remember or recall something like this, right? This is our PERT equation, right? This is our continuous compound equation, right? So A, we have A, which is like our after value, after it's been continuously compounded, after you've done this. And P is our original or our initial value. R is our rate, it stands for rate, right? It's the rate at which something is changing. T stands for time, right? How much is this changing? So these are the same. This is how you learn it in pre-calc, and this is how you learn it in calc. So Remember, the C is our initial value, initial. That's what we start off with. K is our rate. Oftentimes, you'll see the X written as T, but in this case, I simply wrote it as X, but it will still represent time, right? And then Y is our after value, right? So this could be like your value after a certain amount of time, right? So then, now that you understand how you get to your per equation from a proportional differential equation, we can work on some examples. Okay, so let's take a look at another example. So here we're given a differential equation that is proportional to 3 times y, and we're given an initial condition of y equals 2 and that x equals 1. So remember, with our per equation, right, we said that y is equal to c times e raised to k times x. So in this case, we know that remember, we know this is the solution to the differentiable equation dy over dx k is equal to k times y. So in this case, we're given dy over dx is equal to 3y. So if you can visualize this, you can see that k is going to be equal to 3, right? So then we can substitute this with y equals 3. Oops, sorry. With y equals c e to the power of 3x. And then we can solve for our initial condition or we can solve for our initial value by plugging in our initial condition. So we can do 2 is equal to c times e 3 times 1. So then we have 2 is equal to c times e, and then 3 times 1 is just 3. So then to isolate c, we can divide both sides by e to the 3, e to the 3. So then c is equal to 2 over e raised to the third power. Now we can plug in everything, right? So we have y is equal to 2 over 3 over e to the power 3 times e to 3x. So notice how we removed our c value. So now this is a particular solution to the proportional differential equation. And we were able to solve this by finding that, or by knowing that our k value was 3, and understanding the relationship between the proportional differential equation and its solution, right? Its solution. And by knowing this, we were able to plug in values to solve for c. Let's do another problem. In this example, we're given a word problem. Let's read it. The number of bacteria in a laboratory culture decreases at a rate proportional to the number of bacteria present at any given time. Initially, there are 10,000 bacteria in the culture. Due to the environmental conditions, the number of bacteria decreases by 20% every 6 hours. How many bacteria remain after 2 hours? Okay, so we're solving for the amount remaining, which is important to know, right? Because you're not trying to solve for the amount of bacteria that left or that are gone, that decrease. We're solving for the amount that are remaining. That is an important keyword. We also know that it's decreasing, so our k value will have to be negative. We're also told our initial value is 10,000 bacteria, right? 10,000 bacteria, and it decreases by 20% every 6 hours. So k is equal to, all right, sorry, C is equal to 10,000. And we're also told that the rate is proportional. So we know that dy, right, a differential equation that is proportional is going to look like something like this. All right, so this is what it has to look like, where our k value having to be negative. So we can solve for initial condition because we're trying to solve for k, right? Because we're given our per equation, which is our y, or I'll write it in the other term. So we're told that y is equal to c e k times t. Initial condition is 10,000 e, and we're trying to solve for k at time equals 2. And we also need a y value. And to get that y value, we can use this to help us. So at 6 hours, right, so at time equals 6 hours, the amount of bacteria remaining will be 10,000 minus the 20% of 10,000. So we know 20% of 10,000 will be 2,000. So 10,000 minus 2,000 is going to be 8,000. So we know that at 6 hours, 8,000 amount of bacteria is still remaining. So now that we know that, we can set our after result or here, because here, we'll write it here, is 8,000 is equal to 10,000 E at K, and there's 8,000 remaining at 6 hours. So there's going to be K times 6. And we're trying to solve for the rate. So we're going to divide both sides by 10,000 to isolate K completely. So 8,000 divided by 10,000 is simply 0.8 is equal to e to the power of k times 6. And to remove this e, we're going to have to do the natural log to both sides. So this natural log and the e just cancel, and then the exponents just come down. So the natural log of 0.8 is equal to k times 6. And to isolate k completely, we're going to have to divide both sides by 6. Divide both sides by 6, and 0.8 divided by 6. And we get that k is equal to negative 0.0372. And we know that we can check partly that it is correct because in the problem we're told that the culture decreases. So our k value has to be negative, and our k value is negative. We have that t equals 2 hours, right? Because we're solving at time equals 2 hours. So we're going to set our c value, right? Our initial value is 10,000, and then times e all raised to the rate, which was negative 0.0372 times 2 hours, because remember, we're solving for our after value at time equals 2 hours. So we plug that into a calculator, and then we should get, let me scroll a bit, we should get 9,283. So your answer to this problem, this continuous compound problem should be 9,283 bacteria remaining at 2 hours. In calculus, right, we have exponential growth and decay basically just refers to the mathematical models that describe a situation where a quantity is either increasing or decreasing, right, growing or decaying at a rate that is proportional to its current value, which is represented by the exponential function of the form y equals e raised to the k times c, where c is the initial value, k is the constant representing either the growth or decay rate. If it's positive, it's growth. If it's negative, it's decay. And t is the time, which essentially the rate of change is directly related to the quantity itself. And another thing that you must know is that the differential equation that represents the exponential growth or decay is dy over dt is equal to ky, which is your differential equation that is proportionally equal. And overall, the broader application is that exponential growth and decay models are used in various real life world scenarios, like population pyramids, radioactive decay, compound interest in finance, and drug concentration over time. Differential equations pretty much represent the whole world.